Alright, in this video we're going to show you that there are some exceptions to the steric numbers of 4, 3, and 2. They have basically slight differences when we start adding lone pairs to the outside. Those lone pairs on the outside actually take up more real estate than our bonding pairs. So as we start adding lone pairs, we're going to start squishing our bond angles, usually about 2 degrees each time. And we'll see that that really represents a lot of our other families in that situation. So again, we're going to draw Lewis dot structures first. We're going to look for the steric number, or that directional kind of center. Does it have 4, 3, or 2? And then predict our shape and angles from that. So as we look at ammonia, imagine that much like carbon, it's going to have to share a few times. In this case, with 5 valence electrons, it's not going to need to share as much as carbon because it has more electrons to start with. Let's put nitrogen in the middle. Put our hydrogens out to the side symmetrically. Go to the group numbers, whether you like to use 1 through 18 and use the ones place or the Roman numerals, doesn't really matter. You're going to see that hydrogen is in group 1, so it gets 1 electron. Always aim those electrons toward the center. And then nitrogen in group 15 is going to get 5 electrons. Again, aim those singles at each other so they're easier to connect. And then once you have your valence electrons assigned, you can now connect the dots. So here we're connecting nitrogen 3 times so that it's 5 can feel a whole lot like 8, and that noble gas configuration like neon can be achieved through the sharing of electrons and covalent bonds. So what I want to illustrate about an example like this is it's really not a whole lot different than what we saw a moment ago with methane. The reality of this one is this bond down here is going to be a wedge, and it's going to be kind of going forward. This one over here is going to be more like a dotted line, and it's going to be kind of going backwards. And the reason that's the case is because this is no different than carbon, because it still has 4 groups. An issue that most students have, though, is they forget about the 4th group because they forget the lone pairs up here are so huge. And because they snuggle that lone pair in so close to nitrogen, they overlook it and they put it in the wrong group. They would put this in a steric number of 3 in often cases. And that's because they forget about that lone pair that's so important because it is so much bigger. So a lot of students are going to look at this and see kind of that left to hydrogen, right to hydrogen, down to hydrogen process and think, hey, that's trigonal planar. That's a steric number of 3. But they forgot the most largest group, and that's that lone pair that goes up. So that lone pair is actually huge, and that's going to squish. So remembering that this group is huge is super important because that keeps you from misclassifying it. Keep in mind, if we thought this were a steric number of 3, we'd be looking for a double bond, and that doesn't exist here at all. These are all single bonds. We'd expect it to be in the tetrahedral family, and that's the case still. When you look at this one, something unique about it is, sure, it still looks like it has this kind of, pyramid-like appearance, where we have this front face, this back face that are all kind of the same, and then this bottom. But the reality is, because these lone pairs are pushing down, more so on these hydrogen atoms, it actually squishes those hydrogens underneath to make them a little bit more kind of squatty in a sense. So it's going to look more like this because that lone pair is so large. So lone pairs take up a large amount of real estate, pushing those down, and when that happens, you're going to see a bond angle down here gets squished from 109.5 to about 107. So in the end, it looks a lot like CH4. CH4 looked almost identical. It just had a lone pair up front, at least on the nitrogen atom, but on methane, it had 4 carbon atoms, 4 hydrogen atoms around the carbon atom equally. So because there was no repulsion up top, this angle here was 109.5. Because there was a lone pair up here and that lone pair pushes down, we get a little bit of squishing, and that's what we're seeing. So very similar but at the same time, a little bit different. So notice that we do have 4 groups because we count lone pairs. So we're still in that category of 4, just like we were with methane. It's just that that lone pair takes up more space, and because it takes up more space, we get some squishing underneath, turning our 109.5 into about 107. And pretty much any time we add a lone pair, that's going to be the case. Lone pairs lose about 2 degrees every time we add one to that center atom. So as we look at a ball and stick kind of representation of this idea, it looks a lot like this pyramid, this tetrahedron. That's because they're in the same category of 4, the same steric number of 4 when it comes to shape. It's just that because of that lone pair, we have more pushing of the atoms down underneath. So it's like pushing 3 legs of a stool closer together, kind of collapsing the stool in a sense. Now it looks more like a traditional pyramid from Egypt, less like a tetrahedron from geometry. So just imagine that those lone pairs are like 2 big muscular arms, and they're pushing down on those bonds, giving that kind of squeeze play, shrinking the bonding angle, tightening the distance between each hydrogen atom underneath, because that lone pair is so large and takes up so much real estate up top. So you can imagine then as we move across, this continues for water adding another lone pair. So very similar would be the case here, where we have oxygen in the middle. Oxygen in the middle has 6. It's in group 16, Roman numeral 6, and then we have 2 hydrogens. I'm going to not take the bait and draw these a little unsymmetrical, even though I told you symmetrical is always better. The problem with drawing water symmetrically, H, O, and then on the right side H instead of down or up H, is then you start to think that it might be linear if you forget about those lone pairs that are so important. So again, hydrogen family 1 has 1. Oxygen group 16 has 6. And then you connect the single dots only. A lot of good review in this chapter compared to the last chapter in Lewis dot structure. So again, if we were to draw this one symmetrically like I mentioned, but at the same time falls us into a trap, a lot of students that draw water this way are going to see that it looks like a left and a right. It looks linear, and that's not what we want. The reason they think that is because they forgot about the most important features, and that was those lone pairs. These lone pairs are huge, and now they have repulsion on each other. That's going to squish these hydrogens even closer to about 105 degrees. So again, about 2 degrees per lone pair. Now we have 2 of them. So 109.5 down to 107 down to 105 is what we're really seeing. And that's, again, no different than if we were to say this is our little wedge hydrogen forward. This is our little dashed or dotted line backwards. It's very similar to that same kind of sequence that we would have showed earlier. We have this face to the lone pair, we have this face to the lone pair, then the one backwards, and also the one underneath. So it looks very similar again because it is in the same category. It's in that category of 4, that steric number of 4. It's just now that we only have 2 atoms, 2 lone pairs, it's distorting it even further to what we would call a bent shape. So this bent shape is specific to 105, and the reason they call it bent is because really when you think of oxygen and those hydrogens, you're really just bending them really close together, and that's because these lone pairs are out here causing trouble with each other, but also pushing those hydrogens in. So again, one of these is kind of wedged, one of those is kind of dotted or dashed, and because they're so bent together, they just use the name bent to show that kind of perspective. So this is really our last type of shape of 4. We have the oxygen family, the nitrogen family, and then the carbon family all participate in this family of 4 when they have single bonds. Anytime you have a double bond, you're going to be reduced to what we would call category 3, or steric number 3, where you have 3 directions because that double bond's taking up 2 of those directions into the same direction. And then again, triple bonds or 2 double bonds, or even 2 atoms can be in that steric number of 2 kind of direction. So here's kind of a summary of that entire process. Notice we have, from this left side, the different steric number 4s. What we're seeing first over here is going to be the carbon family. And that's because carbon family likes 4 bonds and 0 lone pairs. As you go to a pyramidal, we're going to expect to see nitrogen family atoms. And that's because they have 3 bonds and then 1 lone pair. So notice that lone pair up top changing things. And then as we go down even further, we see that oxygen family. And that's specific when you have 2 lone pairs, but also 2 bonds. So that's a 2 and 2 kind of ratio of how we get to that magic number of 4 that is so important for this particular category. Very rare is steric number 3 when you have a lone pair. The easiest example for this would be something like a nitrite. If you have a nitrogen here, an oxygen there. These are typically rule breakers where we have a double bond, a single bond. And then because we have that double bond, we also have some charges that are kind of hidden behind the scenes that make it even tougher, make it kind of get into gen chem a little bit and difficulty. But it does have that lone pair up top that gives you a little bit of that squish. And unfortunately, they still call it bent. And the reason they call it bent is because we're bending 2 atoms together here. We're bending 2 atoms together in an oxygen family typical atom. So be aware of this other bent. Although it is the rarest kind, it still has 3 directions. So if you think about it, it still has this left, this right, and this up. The up just happens to be a lone pair. It's still in that flat triangle kind of orientation. It's just now that it only has 1 lone pair and a double bond, we lost that oxygen family bent where there's 2 lone pairs and 2 bonds that were both single. And again, that's category 3 there. Steric number 3. And then lastly, what we have is probably one of the easiest shapes. Again, the easiest way to really define what we've seen so far is looking at single bonds here, double bonds here, and now triple bonds here is the easiest way to really think about those. There's exceptions to that as well. You know, you could have 2 doubles, like CO2, and still be linear. You can have 2 atoms and still be linear because you only have, connecting them with either a single, double, or triple bond. It's still the shortest distance between 2 atoms is a straight line. Whether that's 1, 2, or 3 doesn't matter. Recognize that in your triple bond you have the longest bond angle of 180. And then you're going to shrink that 120 that we had here. When we cut a circle 3 ways, you lose 2 degrees for 118 when we add that lone pair. We start out at 109.5, but again, we lose 2 degrees per lone pair, lose 2 more degrees per lone pair, and that's why we see that descending 109.5 to 107 to 105 there. Then we get into polarity, which is a great review for our last chapter as well, and we'll pick that up in another video. See you then.